Hello, this is Jack Hicks, and this is my submission for Lab 6, Magnetic Molasses. So as a quick introduction, the objective is to observe and analyze a system of a permanent dipole magnet falling through a conductive tube of aluminum foil, obtain time data for the magnet and the dimensions of the foil, and then finally, to model the interaction between the tube and the magnet using glow script, plot velocity of the magnet versus time, and compare. So the main ideas are magnetic field of a dipole, magnetic force, flux, and current. So magnetic field of a dipole, the equation is shown on the left, and basically for a bar magnet, it's just good to know that the positive magnetic field comes out of the north end, negative comes out of the south end. So magnetic force due to an object is the force due to a magnetic field and can be modeled using the current multiplied by the change in distance cross product with the magnetic field. Magnetic flux is the magnetic field through an area, and this is the integral of the field with respect to area. But if the magnetic field is constant, it's just the product of magnetic field and area. And flux per unit time is the time derivative of flux. And the current is the charge flowing through something, and it can be modeled by finding the potential difference, EMF, and dividing it by resistance. And all the equations are shown on the left. So as a preview of the results before going into the lab, the bar magnet was found to induce a magnetic field in the tube with the average time to go through the tube being 1.084 seconds after 5 trials, and the model predicted this time to be 17.628 seconds, which does not match well at all. And this is not a calculation error. It's because of the fact that the magnetic moment was taken from lab 4, which may have not been accurate because of the experimental data, again, not calculations. So system was pretty much everything and surroundings was nothing, as you can see on the right. So what models are we going to be using? So we'll use Newton's second and third laws for the update formulas and Faraday's law. And so velocity and position update, by calculating magnetic force on the dipole at every given moment, we can update the velocity and then the position of the magnet in order to model the interactions. And then Faraday's law, we can relate the time variance of magnetic field through an area to the flux through that area. And that allows us to calculate induced current through the area and determine magnetic force. So some assumptions are the origins, the initial position of the bar magnet, assuming the aluminum foil is a perfect cylinder and the magnet doesn't touch it, the bar magnet is a permanent dipole, and these assumptions are made for ease of calculation. The initial values are on the right, which is the length of the foil, the mass, the inner and outer diameter of the tube, magnetic moment, and constants, and the equations are on the left. So getting into the actual experiment, here's a video of one of the trials, and this was done 5 times, and then
Oh my
observed
god.
every time to look at the average time. So taking the data and calculating the average time. So basically, I just went through the video. I looked at when it entered and exit the tube, and then find the delta t for each one, and then add them all together and divide it by 5. So now using GlowScript to model the interactions. So everything on this slide is pretty much just initial conditions, initial constants, and parameters, and also modeling things like visually, which you'll see at the end of the code. So on this slide, starting on the left, we have the formula for a magnetic field of a dipole, and then also we go through every ring and calculate the flux through that ring at any point. And using that and also the force of gravity, we can calculate the force of the cylinder on the magnet falling through the tube. So then the last little bit of the code is still kind of doing the same thing, calculating the net force on the magnet, and then using the velocity and position update formulas to update the velocity and position, and then plotting them. So here are the results of our code. The left picture is while running and the right is after. And so the red part of the magnet is the positive end, making a downward magnetic field. Using the right-hand rule, this means the induced current is clockwise, and using the same method, we can say the blue is counterclockwise. The dynamics of the system do not change when the magnet is flipped, and the shape of the plot shows that the forces acting on the magnet are net zero while in the tube because of a constant velocity, and positive/negative going in and out of the tube. So there's the plot and the time and the visualized magnet. So let's discuss the data. So looking at the data, the observed time of 1.084 seconds is very different than the model time of 17.628 seconds, and this is likely due to the magnetic moment, which was found in lab 4. Now our lab 4 calculations and the calculations in this lab are done correct. It's just that the experimental data was kind of skewed, and so it gave us a strange magnetic moment, which skewed our data here, but the calculations should be correct. And it says for error, I didn't take into account errors in lab 4, again with the magnetic moment. The bar magnets might not be perfect dipoles, the observation times might not be exact, and rounding errors. So as for the additional questions, if the resistivity of the conductor was reduced as close as possible of zero, the resistance would become extremely large and the current would become extremely small. Therefore, the induced current would be small, leading to a small magnetic field and a small force, and the magnet would be much less slowed. And if there are holes and slots cut in the tube, the area would be altered, which means the flux and the EMS would change. So the current would also change. Now that depends on how the holes and the slots are cut in the tube, but it definitely would disrupt the current of the